Yeah, okay, it has started recording. So let me start. So where we actually ended last Thursday. So it was just this slide. That is, we were discussing on an output every layer. So what did we discuss before that is, I mean, I'll just try to briefly summarize. So here we have sequential inputs, and we have seen that, I mean, there are some naive ways to tackle that, maybe just concatenating them as a single input, or basically using the different elements of the sequence as input to different layers. But that also had problem of, say, exponentially increasing the, or rather not exponentially, but it is not scalable for a long sequence. Because the number of number of layers of the network will be too huge if the length of the longest sequence is high. And also the earlier layers, they will be basically trained less because the number of longer sequences may be less, and so on. So we basically decided that, okay, or we saw that another approach is to basically share the weights in different layers, so that those problems will not be there, that some layers getting less trained, scalability issue, and so on. And in fact, I mean, you can have the sequence lengths in the test case or testing scenario more than what you have seen in the lengthier than what you have seen in training scenario. So that also it can gracefully handle. So then we basically saw what are the changes that we require, that is required for the back propagation to work in that scenario. And we have seen that it is basically, you have to accumulate the gradients there, okay, instead of setting. Now we we actually stopped at this after discussing this slide, where there can be an output at every layer. So it is not just an input at every layer. So here we have shown that it is just one single input, but in most of the cases later from next week also, you will see that you will have both, that is input at every layer and output at every layer, that also, okay. But here we have just for easiness, we have just thought one single input. But there are these 4 outputs, and at each step, nothing else happens other than just you are getting output at every layer. So every time step. So HL and Y hat L. So this is Y hat 1, Y hat 2, Y hat 3, Y hat 4. So this first subscript, as I said, it is for the example number. And the second subscript is the element of that sequence. So this is first element of the first sequence, second element of the first sequence, and so on, right? So you first basically have these hidden states, the hidden states from this previous layer. You pass it through a linear layer, that is multiply with matrix and add this bias to get the pre-activation. This pre-activation goes through an activation function to get this new activation. So from HL minus 1 to HL, and then from HL you are getting some output, which can be very simply just linear layer followed by softmax. Okay, so this is just called the readout. Okay, so this is just reading out the output. Okay, could be as simple as linear layer plus softmax. Now we have a loss on each Y hat tail that we also have discussed, that if you are, say, trying to find the captions of an image, so image description. So this is one single input, but the different words are output at different time steps. So these are just elements of a sequence. The sequence is the full sentence, and elements are the words. So if you have a training image and the corresponding caption pair, that is the image and the caption as the pair, then at every position of the word, that every word you need, or you would like to have correct, right? That the predicted word and your ground truth word at every position, you want them to be very close, or rather the perfect one. So we have a loss at each then time step, just the cross entropy loss. Earlier we had in classification scenario at the end, that is at the last layer, this was there only. Okay, but here at every layer you want the classification to be right. Okay, so we have this and classification over all the sort of all the words in the vocabulary. If the vocabulary has 10,000 words, then it is like a 10,000 length vector, right? The probability, that is this. And with that probability and the ground truth probability, which is that one hot vector we have discussed earlier, right? During a normal neural network or connet description. So between those two, you will have the loss. And then ultimately, because the loss is one single scalar, I mean, you can just sum them up or average, whatever these different losses. Okay, so that is where we stopped, and just I'm giving I gave sort of a brief summary of what we discussed last class. Now it is not sort of obvious how to do backpropagation in this scenario, because we have seen when there are multiple inputs what to do, when there are even single input and single output, that is image classification, that we know very well. And then last class we have seen what changes are required for dealing with the case that when you have multiple inputs and shared weights, okay, of the layers. Now this is not too clear what will happen in the current scenario, that is where you have multiple outputs and also the shared basically your weights. So but this is what we saw previously, that is say normal scenario of connet, or rather even with multiple input shared weights. Just only change is that I mean, coming from single input single output unshared weights to multiple input single output shared weights, just one small change, that was this accumulation of gradients. Okay, so this is what we have seen, that I mean, this is just the computation graph representation, that any node, if it is say the functional relationship between the node is like you have one input x and the output is y, and the relationship is fx is equal to y, it might also have some parameter, it might not also have. So parameters, the layers with parameters are what's a linear layer is one of them, and others are I mean, there can be others, but yeah, generally these linear layers are used. What are some layers which are not which do not have parameters? For example, say sigmoid activation function, ReLU, etc., etc. Okay, so these are the three important things: x, y, and theta. Now this is the forward pass. From x you get this y, and in backward pass, at every node you are presented with this delta that is coming into it. Okay, so this delta is del L del Y. So the delta of the loss, or sorry, the derivative of the loss with respect to the output of this node. Okay, that I am denoting as delta Y. And from that you get this delta X, which is loss, that is derivative of loss with respect to the input of the node. And for that, you just multiply the del y del x with this delta y. And for theta also, similarly, delta y you multiply with del y del theta. So this is what we have seen earlier, right? Now, the thing that you need to change is basically, or rather, in this case, we have, I mean, that previous case was sort of a linear chain, or rather chain structure. You have sequential structure. Some nodes, its output go to acts as an input to another node, one single node. That its output actually acts as input to another single node, and so on, right? But here you have branches. So this node can have an output going in as the same, the readout function. Another one is going to the next layer or next time step, right? So you have these branches, right? Here you have output from this layer going in this direction and this direction also, right? So this is what we mean by some nodes can have outputs going into multiple downstream nodes, so branches. So let's say, I mean, this y and this y, the same y goes there. And then, I mean, this can go through some linear layer, readout, etc. Okay, but ultimately, with respect to this node, the same output goes to two directions. Now, so during back propagation, then two deltas come in. So one from here and one from in this y. So let's call them just delta y1 and delta y2. So since there are two deltas coming via these two branches, so I'm just calling them delta y and delta y1 and delta y2. And what I mean, simple thing that you need to do, only thing that you need to do is sum these two deltas for back propagation. So your delta y will be basically sum of these two, and then you do the same thing. So delta y, I mean del y del x multiplied with this delta y. Now, but now here delta y is sum of these delta y1 and delta y2. Initially, I mean earlier you didn't have this, so you your sum would have been just this delta y1. Okay, so this is the only change that you need to do, and the same logic actually applies here that we tried to derive for or using which we tried to derive the gradient accumulation thing in case of shared weights but multiple inputs. Okay, so that's the only change that you need to do. So again, just I'll describe this and then I'll stop for a bit for the questions. So it's very simple. For each node with multiple descendants, so multiple descendants, this one and this one, multiple descendants in the computation graph, simply add up the delta vectors coming from all the descendants. That's the simple rule. So suppose this is one very simple such RNN where you have one single X, it goes through a linear layer, then it goes through some activation, maybe sigmoid, some or tanh or ReLU. But this one, that is the output of G1, which is we denoted it as H1, that is the hidden state, that goes to the next linear layer, getting the pre-activation, then through activation it goes and produces the H2 and so on, right? But here this H1, it also goes to this linear layer, say F1, which ultimately gives you the predicted Y1 hat. This, then you have this loss function, which is just that cross entropy. Okay, so I hope this diagram is clear. So you have X, linear 1, G1, from there you have two descendants, linear 2, from there also you have, I mean, after linear 2, you have G2, G2 also has two descendants and so on, right? Here, ultimately, you have one descendant, G3, and because that is the last time step and so on. So what will you do? You will start with the delta. I mean, the loss is the sum of these L1, L2, and L3, right? This ultimate this loss, and this delta is 1 because del, it is basically del L over del L, right? So that is 1, and then you, if you just see that L is actually L1 plus L2 plus L3, right? And if you take the derivative of the sum, it is just 1. So for like del L1 is 1, del L2 is 1, and del L3 is 1. So just you have the delta value as 1 everywhere, right? Now you have to use your cross entropies delta rule and so on. But you have the delta, right? So you will get the, for example, from here, you will get the delta values here, here, and here, right? Now, once you come here, from there also again, you have the delta values in these three places. Now you see, if you want to compute this delta, you cannot do it because you don't have this delta yet, right? But you have the delta here, so you can compute the delta at this position, which in turn will enable you to compute this delta that was missing earlier, right? Now you have this delta and this delta, so you sum them, and then again the same back propagation. So this delta and so on, right? Hopefully this thing is clear. I'll just stop for a bit if you have any questions before I move to the next slide. Summary, I mean, what we have discussed till in this like 10-12 minutes is what will happen to the back propagation rule if we have multiple descendants or multiple outputs. Okay, so the simple rule is that you sum the deltas and then do the same back propagation. Any questions? Yeah. Okay. If not, then let us go ahead with more, some more rather application scenarios where we can use this multiple input, multiple output, or even one single input, multiple output, different combinations of either multiple or single. So this is one thing that we have been seeing a lot till last week, that is one-to-one classification. So you say image classification, you pass in one image and you get the class levels, right? So that is one-to-one sort of. Okay. Now what is one-to-many? So one-to-many is an example is image capturing. That's what I have told earlier also. So you have one image, from there you have you can generate captions which have multiple words, right? That's one application scenario. Now what is many-to-one? This is sentiment analysis or video action recognition. So you give the different words of a sentence as input and you get the sentiment. I mean, whether it is sad, happy, neutral, etc., etc. Okay, there may be many other classes also, or even video action recognition. Some video you are passing it through, and by video you mean, I mean, the elements of the sequence in the video are the frames. So video is just a collection of frames. So you are passing the different frames and you are ultimately classifying it as whether, say, somebody is running, somebody, I mean, what activity is going on. Somebody may be running, somebody may be jumping, applying makeup, so on and so forth. So this is many-to-one. Now many-to-many. So many-to-many is machine translation. Suppose you want to translate from, say, Bengali to English. So you give these Bengali words here and as an output. I mean, after some steps, when the Bengali words are I mean done for the sentence, you get a representation which is sort of summarizing the total I mean the whole sentence, and then you I mean this is sort of encoding the Bengali sentence, and then you are you have that encoded representation of the whole sentence, which then is decoded here into different words of English. So this is many-to-many. We'll see most examples of these things later, but just to give you an idea how we can use these sequence to sequence models. I'm just telling it. Now the last one, which is many-to-many. So one of them is tracking, basically that you are giving some input video frames and you want to basically track one person. So that is the output. I mean, what is the bounding box that say one person is say walking, so where it is in the frame, and that is the tracking problem. Image classification, though it may not seem very obvious how image classification can be basically many-to-many, but we will actually see probably that will be the sort of last class where image classification will be many-to-many. How can we do that? I mean, using attention and so on. Okay, so there are other ways. I mean, transformer that we will see in this week, but maybe vision transformer we'll see next week. Okay, so these are some examples, sort of application scenarios. Now, one very sort of grave problem in RNNs is this, that RNNs are extremely deep networks. I mean, whatever we have seen as examples in this last lecture or this lecture, we have considered sequences of length, say 3, 4 max. Okay, but it can have 1,000 length sequence, even 100 length sequence words. I mean, a whole paragraph may be required to be analyzed for sentiment, okay, or summarized. So it can have 1,000 element sequence. So this means basically back propagating through 1,000 layers, right? So though they are shared, but you are giving input to every layer. So when you are back propagating, it's going on like this, and that will mean back propagating through 1,000 layers. And back propagating, as we have back propagation we have seen, is just an intelligent use of chain rule. So basically what you get via chain rule, you do it in an iterative way. So ultimately, if you want to have the derivative of the loss with respect to the parameters at the first layer, you have to start from, say, the nth layer where n is 1,000, right? So del j del n and so on, and it goes like this. Now this means that you are multiplying a lot of these Jacobians or derivatives, right? So I mean, if you just think about scalar loss and just one single parameter at every layer, just one single parameter is there. By that, what I mean is that everything you are dealing with, say, scalar even, then also you are just multiplying a lot of scalar derivatives, right? So what will be the scenarios? Let us see. So multiplying many numbers together can mean these three cases, or one of these three cases. If most of the numbers are less than 1, we will get 0. And this is where is usually known as vanishing gradients. So if all these gradients are very small, then exponentially it gets multiplied, right? I mean, if you have 100 such parameters, and these get, so hundreds of such variants, derivatives will be there. It may be, I mean, in general, it is basically the Jacobians, because this is vector and this is also vector. So you will have a derivative matrix, right, which is called the Jacobian. So they will basically be give rise to very small values. I mean, you can just intuitively think it in terms of scalars. You are multiplying a lot of small scalars. So ultimately you are going to get a 0. Similarly, if you are multiplying with numbers which are more than 1, then you are going to get infinity, which is exploding gradient. So if the gradient values are pretty high, then you are going to get a very large step, because ultimately the gradient is giving you the step value, right, in that gradient descent algorithm. So you may just overshoot the minimum. And if all numbers are close to 1, then we get a reasonable answer. So that these are the three scenarios. Now, exploding gradients could be fixed with gradient clipping. That is easy. I mean, if all numbers are more than, say, 1, so you can just clip it at some values close to 1, and that tends to work reasonably well. But vanishing gradients are bigger problem. And intuitively, vanishing gradients prevents gradient signals from later steps reach their earlier steps. So suppose you actually have something in the, say, third step. You have this 1000 time step long sequence, and something is actually very important in that third step. So maybe you have a very long sentence of a movie review, say the Kramer versus Kramer movie which is starred by, say, Dustin Hoffman and Meryl Streep, shows some issues in parenting and so blah 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 blah, which is a very good movie, something like that. So this that movie, I mean, at the end it is referring to that movie, that information may get lost, and maybe that, okay, ultimately it is a good movie, but in the middle maybe there are some bad review of it, maybe that, okay, the photography was bad or something. So that this which is related to what, this thing may not come. Why? Because if the gradient is vanished already, I mean, by backpropagation, you are coming from 1000 to 999 to 998, all those delta values, and you are multiplying very small values, and ultimately when it reaches there at the very sort of left, very beginning, it may not get a good gradient signal. So the update will not be happening for those parameters, the parameters that is dictating the very first layer. So now that can basically be a problem, because if you are changing that input at that timestamp, if your parameters don't get changed as a result of that input, then sort of it gets independent of that input. So whether you are giving it as the movie that I told or some other movie, but all the other information remaining same, it will not matter much. And that's a big problem. I mean, the gradients don't reach the, I mean, I have probably just tried to give one contrived example, but if it is a very long, I mean, just abstractly thinking, if it is a very long sequence and you don't get the gradients at the very beginning from the ultimate loss, then something that you change at the beginning will not affect the loss. So that is sort of the abstract idea, and that's where basically most of the problems, I mean, that's why actually RNN, though the idea is very slick and maths works out good and so on, it was not popular so much. this prevents RNN from remembering things from the beginning. So that's sort of the idea that, okay, I mean, whether I gave some input 1 or input 2 as the say first element or second or third element of the sequence, it just can't remember when it is computing the loss and so on. Okay, so that's sort of the basic problem with or sort of yeah, the basic problem in RNN. So what should we do to promote better gradient flow? So I will go to there, but if you have any questions, you can please ask. We will go into one sort of popular architecture, I would say, but we will see. I mean, it may seem a little arbitrary, but we'll see. The LSTM long short term memory. But if you have any questions till this part, you can shoot up. Okay, if not, then let me go ahead with it. Okay, so I've seen that the basic idea that we would like the gradients to be close to 1, because that gives us some reasonable answer. Otherwise, either exploding gradients or vanishing gradients would be the problem. For Jacobians, that is for vector valued input and outputs, this means that eigenvalues will be close to 1. So this is for scalars, and this is in general for vectors. But first, a bit of notations, because we will soon run out of sort of notations. We are just trying to compactify a few notations. So each time step, this was happening. Suppose you were having the input at every time step, that is multiple inputs. You have the output activation from each layer. You are concatenating them, and then concatenated vector you are passing through a linear layer to get this pre-activation, which goes via this activation layer to get the activation value. So from HT minus 1 and XT, you get the HT. And I am saying this whole relation just expressing as Q. So HT is Q of HT minus 1 and XT. Okay. So this is the RNN dynamics. I'm saying that this is the RNN dynamics because from the previous layer's activation and the input at the current time step, you are getting the activation at the current time step. So this is sort of the dynamics followed by RNN, and I'm just denoting these dynamics by Q. Okay. Now, okay, so it says that base gradient flow is when the dynamics Jacobian is close to identity. So that's what will ensure that it does not explode or vanish. So however, so this is important. However, it depends on whether you want the RNN to forget the past or not, because it may be that in some sequences it is actually I mean, those very long dependency what the words of past or elements of past that is not required actually. I mean, whatever is ultimately your sentiment or whatever the activity that is going on in the video, that actually can be classified actually very good from the last part of the video or last part of the sentence. Okay, so whether you want to forget or want the RNN to forget the past or not, that is also important. So you have to have some learnable way. It is not that you will always force this this to be true. So you have to have some learnable way. I mean, depending on whether you want to forget or not, it will decide. So that let us see what we can do. So it's this. I mean, Sergey Levin, as Sergey Levin says, I mean, it's a funny little neural circuit that does it. So we'll see. So again, I mean, I'm just following Sergey Levin's lectures in this sequence to sequence models. They're great and fantastic. Okay, so we want this, right, from the last slide, if we choose to remember, because that's the thing, that whether it depends on whether or not we want to remember. So if we want to remember, then we want this, and this small i's basically mean the elements of those Jacobian or derivative vector. Okay, so ith element of that derivative vector or Jacobian. Okay, so yeah, so a little neural circuit decides whether to remember or overwrite. So let us see. So we actually introduce or This actually is introduced in something called long short-term memory, so LSTM, and they have introduced basically two outputs from previous time step, but we will come to that. Let's say they have introduced something called a cell state. So this is from the previous time step, which is CT minus 1. I am just denoting it with this. Let's see what happens to this. So to the CT minus 1, we are employing some, or we are multiplying it with a number between 0 and 1. We are calling it as forget gate. Why forget gate? Because if ft is close to 0, that means CT minus 1's value, that is a previous cell state value, is forgotten. We will see how we will get the new cell state value, but at least the previous state is forgotten. When ft is 1, this means we don't want it to be forgotten. We want the cell state to be remembered. Okay. So this is obtained by multiplying the CT minus 1 value with this ft, which is a value between 0 and 1. So if CT minus 1 is a vector, which is generally the case, then ft is also a vector, and the multiplication is element wise multiplication. So it may be that, okay, some element of the CT, that is say the first and fifth and ninth element of the vector, that I want it to remember. So for those, the corresponding ft will be close to 1, and for the rest it will be 0, the ft values. So if something in between, I mean ft's value is something in between, then also you can crudely think that, okay, ft emulates this nature, that okay, it's sort of binary. So it's a little bit arbitrary, the design, but it works well. So that's why, I mean, it's just I'm trying to make some sense out of it by giving these analogies of binary gates and so on. Okay, I mean, you cannot completely make it binary, otherwise it will not be differentiable, back propagation. Okay. So, okay, so the summary is that if ft is, that is forget gate's value is 0, its value is forgotten, the previous cell state. If it is 1, then the value is remembered. Now we will see how we get the modified value. So so that is given by this gate value gt. So ft is 0, that we have seen, if tends to 0, it means CT minus 1's value is forgotten, and it is overridden by GT. So whatever is GT's value, GT is a value which is between, generally a small value, which is between -1 and 1, and that you basically add to it. So if say ft is 0 and GT has some value, then CT minus 1's value is overridden by GT. But if say ft is 1 and GT is 0, then actually CT minus 1's value is remembered. And if say ft is 1, that is this, and GT has some value, then the value gets modified. So CT minus 1's value get modified in an additive way. So the modification is done in the form of an addition. So it just adds a small value to CT minus 1. And that's how you get the basically the new cell state. So this is the new cell state. Okay. So what is the equation that basically gives this new cell state? This is of only CT is equal to ft into CT minus 1 plus GT. So ft into CT minus 1 and GT, with ft is between 0 and 1. And we'll later see that GT is also between -1 and 1. So it is actually a very now well structured compared to what we have seen, how we get say HT from HT minus 1, that is the RNN states. So it goes through some non-linearity again, I mean linear function, then non-linearity, and there is no non-linearity here. So the CT and CT minus 1, that relation is linear because it just gets multiplied with the value and gets added with the value. So it is not going through any tan H or any other say ReLU type nonlinear function. So it's more structured. I mean, there were concepts of say highway networks earlier. I mean, sort of people say that, I mean, these Lstms and they have been taken, but they were contemporary from these basically ideas, but yeah, let's not go into that. It's just that, okay, it is more structured, it does not have these non-linearities, and what this allows is that the derivative, so the derivative is ft only, so del qi by del ct minus 1i. So I is basically the ith element, as I said, and q is what we have defined q, that that is the RNN dynamics, right? So basically the q you can think as this one, this ct. Okay, so that the derivative is ft, right? So that is the RNN dynamics. Now, of course, the question is, where do we get these ft and gt values? Who will tell that whether ft, I mean, we want to forget or we want to keep it intact, right? So that's a big question. Where do we get this ft and gt? And that's where this other path of the Lstm. So we'll see what is the long path and what is the short path, but this is the other path that helps. So ht minus 1, you can think that it is the RNN output at previous time step. So I said briefly when I started to introduce this ct minus 1 that you get two outputs from the previous time step. One is the cell state, another is this hidden state of the RNN. So though it is not RNN, I mean, we cannot technically call Lstm as an RNN, but just so that you can sort of go back to your sort of RNN, I mean, go back and put your RNN hat on, so that these H and these notations are a bit familiar with you. I'm just saying that it is the RNN output, but maybe just you can think that it is two outputs that is coming from, say, the previous Lstm state. Sometimes they are called Lstm cells also, but just, I mean, just to forget about all the confusion, we can just think that, okay, this is output from previous time step. Output from whether Lstm RNN, you don't need to bother about. So previous time step has two outputs. One is ct minus 1, one is ht minus 1. Now this ht minus 1, we will deal it with this very similar way as we did it RNN. So you have the input at this current time step, you concatenate them and pass it through the linear layer. Okay, so that is the equation. So w into the concatenated vector plus b. Now you will notice that I have written these 4 parts. Okay, and all of them are vectors. So earlier, what we have got earlier is this output, that is only this output. This has the same dimension as ht minus 1, because this was giving me the ht. So the dimension of the output and this ht minus 1 were same. What we are getting here is 4 times that dimension. So each of these ft bar, it bar, gt bar, ot bar, they are of dimension equal to ht. So this w has rows which is 4 times the number of rows that we earlier had for an RNN. Hopefully this is clear. I'm just giving you, say, 10 seconds time to digest this thing. Okay. Maybe just a summary that earlier you were doing the same equation, but you are getting the output as the same dimension of ht minus 1. These two this dimension and this output dimension would be same. Here you are getting 4 such vectors. So that's why this w is now 4 times, or number of rows is 4 times, okay, than the previous one. Now, what you will do with each of these vectors, that will now come into. So first you take this ft bar, and here you see that this is ft bar. So you are basically, you will somehow use it to get the ft. And how do you do it? So element wise, you employ a sigmoid function. So all the elements of this vector, you pass it through the sigmoid, and you get such, as a result, a vector which is the same dimension of as ft bar, which in turn is the same dimension as ht minus 1 or ht, and this ct minus 1 also, because they have the same dimension that I forgot to mention. You can make it different, everything, but I mean, these are sort of the choices that you stuck into the literature, and it worked well. But let us just think it as a rule. So every element of this ft now, so this is basically the ft bar, every element of this ft is then between 0 and 1 because you are passing it through the sigmoid function. So this acts as the forget gate. So what did we start with this slide, that where do we get the ft, gt, etc. So you are getting it from this previous, the second output from the previous time step. And the non-linearity you see is involved in here. There is no non-linearity from CT minus 1 to CT. Okay, again, go ahead. Let us go ahead. The second basically output of this operation is IT. So IT and this GT, they will give me the additive modification that we were saying earlier, that okay, this path, I mean, FT decides whether it will be forgetted or not, and will you forget or not, and this is the additive modification. So for that, again, IT bar is passed through a sigmoid value, which is again makes these elements of IT bar all between 0 and 1, and we are calling it as IT, the input gate. Okay, now you have the third one, this GT bar. So GT bar is then passed through the 10H activation function. Now these all may seem a little arbitrary, but again, as I'm saying always, that it works well. You can change it to say sigmoid or even ReLU, but yeah, I mean, the reason that this design stuck with is because of historical reason. It is not from today. I think it is something somewhere in 90s this Lstm came. It was way ahead of time. So at that time, ReLU and those activations were not even in picture. So these activation functions were there, sigmoid, 10H, etc. So people played with it. So you get from this GT bar a GT which is now between -1 and 1. So all the elements will be between -1 and 1 because it is 10H. Here you see you got values between 0 and 1. Now you are multiplying this GT with this IT. The idea of the input gate is that whether you want to modify this. If you don't want to modify this, then IT will be 0. And so whatever will be the GT's value, it will just 0 will be added. So if you want to completely forget and make it 0, then this is 0 and this IT will also be 0. That is the idea. And if you want to basically modify, then this IT value will be 1, and then the modification value will be given by this GT. So it is not just GT, it is this IT into GT. So whether you want to modify and with what value you want to modify, right? So this way you get your ITs and GTs. What is the role of this OT? This basically gives you the next HT. So with after getting modified by some linear or non-linear activation value, that is function, activation function sigma, that is this OT bar, it goes through this. So this is basically OT bar goes through this, and OT then as a result is 0 between 0 and 1, and this gets combined with this CT, which again comes through this 10H to give you the HT. So again, I'm again probably telling that this may seem a little arbitrary, but the major thing is actually the forget gate. So if you want to forget or not, and this actually dictates this relation from CT to CT minus 1 to CT, and that is sort of basically makes this Lstm to work. Mostly people say. Okay, so this is the HT now. So we have seen from CT minus 1 how to get CT, and HT minus 1 to HT. And the difference between these two paths is that CT is more straightforward, just linear operations, but HT has all the non-linearities and so on. Okay. Another one, just small thing, that is this. I mean, you can, because you say, see, this is why. So you can you would like to have maybe, or you may like to have outputs from every time step. So how can you do it? From HT, you just pass it through some decoder, so which is the readout function, maybe just linear layer plus softmax and so on. I mean, you can even have different other fancy activation functions and so on, but it is just from HT that the hidden state, you get the output at each time step. So this sort of gives you the high level overview of LSTM, how it works, why it sort of does not have the disadvantages of RNN and so on. But this question is always there. Isn't all these a little arbitrary? And what is the answer? It is yes, but it ends up working quite well in practice and much better than naive RNN. So this is the sort of thing. And one of the reasons that people have come up with is because this path is pretty much straightforward. Now, so there are two paths then, this path, and these are basically the long path and short path that is sort of denoted as. So CT's relation is this, and it changes very little step to step because you have only FT here, right? That basically dictates the change, which is between 0 and 1, right? And GT is also very small, between -1 and 1. So it just changes slightly. That's why it is long-term memory. So if it changes slightly, that means it's long-term memory. And this changes all the time. It is multiplicative and short-term memory. So it has lots of complicated operations going on, non-linearity, etc. So it changes all the time, and that's why it is called short-term memory. And that's why this whole thing is called long short-term memory. Okay. Oh, sorry. Now, these are some practical notes. This is the last slide. That's why I'm not giving a break here. This is some practical notes. And I mean, after describing this in brief, we can stop for questions. So in practice, naive RNNs almost never work. So because of this vanishing gradients or exploding gradients problem, mostly vanishing gradients, LSTM units dramatically improve over naive RNNs. So if you have to choose a sort of go-to for your sequence to sequence problems, so you can choose LSTM as a go-to over RNN. Requires way more hyperparameter tuning, this clipping, this learning rate of different layers and so on, the dimensions, than standard fully connected or convex. They are probably, I mean, the complications are less. Some modifications and alternatives work better for sequence. We will have detailed discussions on transformers. We will not have discussions on gated recurrent unit, but this is sort of another popular one, but not so popular like LSTM. It gets rid of, I think, one of the gates at least. I mean, the output gate it gets rid of, and the output is directly read from that CT, the top long-term memory. So that is the thing. I think I will conclude this RNN LSTM discussion here. We will start with attentions next lecture, which is Wednesday. But if you have any questions on this, please ask. I'm allowing you to unmute. No questions?
Sir, actually, in the previous that dynamics Jacobian, like del Q by del HT minus 1 equal to 1. So what is the Q value here?
Oh, Q is defined, I think, pretty earlier. Yeah, this is where I am defining Q. So I'm just telling that instead of writing this three equation, so which is connecting this HT minus 1 and this XT to this HT, I'm just writing everything as just a function Q. So Q you can think of as G of this thing of this thing. Okay.
Okay, sir. And sir, and that thing that there are many vectors are stacked like OT. So can you please repeat that what does that vectors are significant which is to stand for? Actually, I got confused.
Yeah, it's a little confusing, the whole thing. It's a little arbitrary, but
this one, sir.
Yeah, I will go to the last one, the very last year, which will. Yeah, I think what happens is that when you, I mean, earlier what you were doing is this thing only you were doing to get the AT, I would say. and then you are doing G of AT to get the HT, right? So this is basically AT that you were getting earlier, right? Then AT you were passing through the nonlinear activation functions to get the HT, right? That's what I have told in that Q definition, the slide where Q were defined. Okay. So this AT, and I mean, this is an element wise operation. So it is sigmoid or tan H over all the elements of AT. So the number of elements in AT and number of elements in HT is also same, right? Now, since this is HT, that is value of H at time T, and this is value of H at time T minus 1, the dimension should be same because ultimately it is H at T and H at T minus 1. So basically, the dimension of HT is now what we have seen is dimension of HT is same as dimension of AT, and dimension of HT is same as dimension of HT minus 1. So basically dimension of AT, that is this, and the dimension of HT minus 1, they are also same. That was the original case in RNA. But here what it is shown or said that you get this W. Suppose I'm just taking some ballpark value. So HT minus 1 was say 100 dimension. In that case, W is 100 by 100 matrix, or rather, if it is HT minus 1 is 100 and say XT is 50, just for the timing I'm saying. So then it is 100 by 150, right? Because ultimately this W, this is the dimension of W, right? So it will give AT as a 100 by 1 vector, right? What these guys are telling that in LSTM, each of these is 100 by 1. This is 100 by 1, this is 100 by 1, this and this. So in that case, W has to have 400 by 150 as the dimension, right? Did you get it? I mean, at least.
Sir, 400 into 150, why? Because
Why 150? Yes. Why 150? Because H is 100 dimensional and XT I have taken 50, right? XT can be 100 also. XT can be anything. So I'm just taking XT as 50. So you are concatenating them, right? So your HT minus 1 had some value, big vector. Your XT is another big vector, which has 50 elements. It has 100, right? So it will be 150. I mean, the concatenated.
Oh, got it.
Right? So this W is then 100 by 150. If W is 100 by 150, AT is 100 by 1. HT is also 100 by 1. But what we are saying in LSTM, we are not multiplying with a W which is 100 by 150, but 400 by 150. So whatever, I'm not telling it as AT, whatever is the output of this operation, which is this, is 400 by 1. I'm just saying the first 100 is FT, the second 100 elements is IT, third is or bar, IT bar, FT bar, IT bar. This is third 100 elements are GT bar and fourth 100 elements are OT bar. Okay, and then you are taking these 100 element things and passing it through the sigmoid, tan H, sigmoid, etc. Is it clear?
Yes, sir. Now it's clear.
Okay. Any other questions from anybody?
Sir, the number of parameters in LSTM cells are quite larger than RNN cells, right? So, like, is there a significant effect while training LSTM cells as compared to RNN?
Yes, it takes a lot of time. I mean, compared to RNN, but sort of people tend to go for LSTM because the performance is very, very good. So RNN, even though it trains comparatively faster than LSTM, the performance is not good. Okay.
Also, since it has so many parameters, will it not be sensitive to overfit easily?
Yes, exactly. So that's
how
why.
is it handled in that case?
Yes. Sorry, what?
So how do we handle the training in LSTM if it's sensitive to?
Yeah, it's basically you have to have more data. I mean, how do you handle overfitting? So you have to, I mean, the best way is to have more data. That is, suppose you are training a image captioning system. So you have to have more sort of paired data, training data, that is image and text data, that is image and the caption, that you have to have. drop, I mean, other regularization regularization techniques that you can employ. For example, dropout plays an important role here. Even other regularization, L2 regularization, but dropout seems to be very sensitive. I mean, this one is very sensitive to dropout. I mean, choosing dropout value enables it to do good. Then augmentation, data augmentation, and so on. So these are very data hungry. That's true.
Yes. Thank you.
Any other questions?
Sir, maybe one last question. Generally, what we have, as you pointed out, RNNs, we cannot have a very long sequence due to vanishing gradients. But even in LSTM, uh, can we really do beyond, say, 15 to 20 sequences? I mean, what
length.
has been your experiences with?
Yeah, I mean, the length of the sequence you are saying, right? The number of.
Yes.
Yeah. I mean,
Yes.
generally people do these things using LSTM. I mean, GRU is better in a sense. So I think this also connects to Devajyoti's question also. GRU only has 2 gates, if I remember it right. I mean, definitely output gate is not there. I think the IT gate is not also there. What will that mean is that W is now 400, not 400 by 150, but 200 by 150. So you are reducing the number of parameters, and that way GRUs not only train faster, but also rather works well in terms of less overfitting. So, and then coming back to Kaushik's question, I think people have used like 70 length, 75 length sequences pretty easily. But as you can see, I think I mean, if you want to increase the data length, you have to have more data also. So these are very data.
Okay.
I mean, what we will see later also, the transformer architectures, they are probably the most data. So that is true.
Yeah, because, sir, I mean, in a way, counter question, and this was also related to the paper which you had given us,
Yeah.
that if you have a very long sentence,
Mm-hmm.
still the deep learning struggles to understand the entire context and kind of remember what was said in the early part of the sentence and relate it to the last part. And a long
Yes.
sentence would probably mean like 25 words, 30 words,
Yeah, I
and
mean,
still
by
if
long
they struggle.
sentence, it may be that it is, I mean, long paragraph also. I mean, maybe that a paragraph is 4 or 5 sentences long, and you may need to say find the sentiment of the paragraph, or from that paragraph maybe the review, say
Okay.
recommendation system. So long sentence, of course, I mean, you will probably not get very long sentence of 75 words, but you can get like a paragraph of 75 words, right? And then not only sentences, videos, maybe or audios. I mean, there are no dearth of long temporal sequences, not only just sentences. So that you will get.
Okay. Understand. Okay.
Okay.
Thank you, sir.
Okay, thanks. Any other questions from anybody? Okay, if not, then yeah, let me end this meeting. Yeah, thanks a lot for making this so much interactive. We'll meet again on Wednesday.